In this unit, we're going to look at exponential functions. In this lesson, we're going to look at solving simple exponential equations.
All right, hi everybody. So in this particular lesson, we are going to be solving exponential equations. But we're going to be solving a very special type of exponential equation, one where there's some relationships between the expressions that we're seeing in the equation. Okay, so just to introduce it here, exponential equations are equations where the variable is in the exponent. Okay, big important point there. The variable is in the exponent. We typically label equations by identifying where the variable is. Now, sometimes that gets a little bit complicated. So, I mean, this is just in general here. So in this case, we're going to try to find out what that exponent is that makes the left side equal to the right side. Here, for this lesson here, the way we're going to do it, our method here is to make the bases the same. Okay, I'm going to show you what happens when we do that. Now, before we get to that, let's take a quick look here and see about what that means to make the bases the same here. So we'll do just a little bit here, and then we'll get into the actual solving here. So to convert to the indicated bases here, sorry, that's what it says here, convert to each to the indicated bases here. So we want to convert 9 to the 2x to a base 3 expression. Well, okay, this is 9 to the 2x. So what I'm going to do here to start off with here, and actually I'll change colors. Okay, this is going to be 9 to the 2x. But what I want to do is I don't want to write the 9 anymore, okay? So I'm going to replace the 9 with a power of 3, but it's still all to the 2x here. 9 is going to be 3 squared. So I haven't done anything. It's still 9 to the 2x, but I have changed the way I've represented that 9. And when I do that, what I can do here is now I've got a power of a power, so I can multiply the exponents, and 2 times 2x is 4x. So the expression 9 to the 2x could actually be written as 3 to the 4x. Just like in this next one here, I've got this as 81 to the x minus 2, but I no longer want to write 81 there. I'm going to get rid of that. What I want to do is I want to replace it with a power of 3. And I know that 81 is 3 to the 4. Now here there's a very prominent or prevalent temptation to want to do this. I've got power of a power now, so I need to multiply the exponents. Very, very common mistake is to write it as 4x minus 2. And the mistake is that it's 4 multiplied by x minus 2. It's 4 multiplied by x minus 2. I need to distribute that exponent. So it shouldn't be a 2 there. It should actually be an 8. So 3 to the 4x minus 8. I mean, it's just a very common mistake to forget to distribute the 4 there. Just want to make sure that you've seen that. On the next one, notice that I've got 2 different numbers here that could be powers of 2. I've got the 8, and then I've got this 16 to the x. But what I want to do here is I want to rewrite that 8. So it's going to be 2, well, 8 is 2 cubed. 16 is 2 to the 4. Okay. Now, I'm going to work with that power of a power first. So I've got 2 cubed. And when I've got a power of a power, I multiply the exponent. So 2 cubed to the multiplied by 2 to the 4x. And now I've got power multiplied by power. The bases are the same, so I'm just going to add the exponents together. And I'm going to change the order. I'm going to put the 4x first plus 3. So 2 to the 4x plus 3 is the answer that we're looking for right there. Okay. Let's look at the next one here. I'm going to change this to a base of 2 here. Now, notice that I've already got a 2. And then I'm going to replace that 4 to the power of x here. What I'm going to do here is I'm going to take and replace that 4 with a 2 squared. And so now this becomes 2 multiplied by, and I've got a power of a power, so I'll make that 2 to the 2x. And then when I multiply these 2 powers together, I've got to add the exponents. The common mistake that gets made here is to forget that a 2 by itself is going to be 2 to the 1. In fact, the more common mistake made here is that people will actually multiply those 2 2's in the bases together here to get 4 to the 2x. But actually, this is like 2 to the 1. So when you multiply 2 powers together, you add the exponents. Okay, the base stays the same. As long as I got the same base, the base stays the same. Over here, 9, and I've got this 27 to the x minus 1. So 9 is the same as 3 squared when I write it as a power of 3. 27 is 3 cubed when I write it as a power of 3. There's not much I can do with that 3 squared right now, but here I can take that exponent and distribute it through. And remember, to distribute it through, it's 3 multiplied by x minus 1. It's binomial, so it has to get distributed through. And now I'm going to add the exponents together because I have the same base. So this will be 3 to the, okay, well, I got to put the like terms together. I've got a 3x there, and there is no other term with an x in it, so that's okay. But I've got 2 plus the negative 3, and 2 plus negative 3 is going to be negative 1. And then here, well, in this case, they've actually put the parentheses around that for me, so I don't really need to. But I've got to rewrite 1 over 16, though, as a power of 4. Now, because it's in the denominator, I know that that's going to be negative, okay? And 16 is 4 squared, so it's going to be 4 to the negative 2. And then I've got a power of a power, so I'm going to multiply those exponents through. And so it will be negative 8 plus 2x. And actually, I will probably be very tempted to change the order just so that it's in, like, I guess, standard form for that polynomial there, right? Want the x's to come first there. So that is the tool that we're going to use to help us solve the following equations here. So here's the kind of the procedure we're going to follow right down here. So to solve exponential equations, what we're going to do is we're going to write both sides of the equation with the same base. And then there's a bit of a misnomer here. A lot of people call it canceling the bases, and we're doing that there because it's such a common way to write it here, say it. But actually, there is no such thing as canceling the bases, okay? There is no such thing as canceling the bases. But what we're going to do is we're going to work with only the exponents to solve for x here. This isn't canceling the bases so much as it is logic. Okay, there is a logic step that we're going to follow here, and I'll explain it when I get to it when we start working through these equations. Let's start to take a look at some of these examples of equation solving so that you'll have that as a tool moving forward. Okay, here we go. Let's start solving some equations here. So this first one, notice we've got 3 to the x is equal to 81. So what we're going to do to start off with here is we're going to rewrite everything there as with a common base. And in this case, well, 3 is as simple as it's going to get. But 81, okay, well, 81 is the same as 3 to the 4. Now, as soon as we've got a power equal to a power, and the bases are the same, now I want you to think about this. A power consists of a base and an exponent. So maybe I put like base and exponent there. That's it. It's just got 2 parts to it. So if I've got 2 powers that are equal to each other and the bases are the same, then it must be the case that the exponents are the same. Now, you might go from here to here and think, well, didn't you just cancel the bases? Well, okay, no. Canceling suggests like a division where I divided them out and I got 1 here. Or I did something like, I added and got because I had the additive inverse, something canceled and became 0. But that's not what's going on here. What's going on is I'm looking at this and I'm seeing a power equal to a power, base is equal to the base, which means the exponent must equal the exponent, which isn't really canceling. It's not really an algebra step. That is more of a logic thing. If the whole is true and the majority of the pieces, if the wholes are equal and then the pieces are like the bases are equal, then the exponents must be equal. So for this next question, I've got 2 to the x. There's not much I can do to that. But we've looked at this one before here. If I've got the square root of 2 here, I can write that as 2 to the 1/2. And once I've got power equal to power, as long as the bases are the same, I know that exponent must equal exponent. And so I know that x must be 1/2. Okay, here it's going to be a little bit more complicated just because there's a binomial here in the exponent. And it might not be abundantly obvious that 343 is going to be 7 cubed. Okay, that takes a little bit of comfort, okay, with these this information here and these powers here. But you could certainly play with it in your calculator because you'd very likely suspect that it must be a power of 7. And now, because powers are equal and the bases are equal, I know that x minus 2, the exponent, must equal 3. And then I'm simply going to add 2 to both sides of the equation to get that x is equal to 5. And that's my solution. In this next row, I've got 5 to the 4x plus 2. There's really not much I can do with that. But the 25 can be written as 5 squared to the x. And so we get 5 to the 4x plus 2 is equal to 5 to the 2x. Just move this up just a little bit here. And then I've got power equal to power. The bases are the same, so I know the exponents must be the same. And now maybe I would bring that 2x over to the other side here. So it'll be 4 minus 2x is 2x. And I'll subtract 2 from both sides to get negative 2. So basically, just in case you missed that, so what I did is I subtracted the 2x and then I brought the 2 over. And then I'm going to divide by x. Sorry, not x. I'm going to divide by 2, the coefficient here, to get x is equal to negative 1. Actually, I'll write that down just a little further down here so it's more clear. So this will be x is equal to negative 1. For this next one, the common base here is likely going to be 2. So this is 2 to the x minus 1. Can't do much with that. But 4 can be written as 2 to the 2 to the x minus 2. So 2 to the x minus 1 is going to equal, well, now I've got a power of a power, so I distribute the exponents. So 2 to the 2x minus 4. And then from there, because I've got 2 powers equal to each other and the bases are the same, I know that the exponents must be the same. So now I'll subtract the x to bring it over, and I'll add the 4, and we'll get that x is equal to 3, or 3 is equal to x. Over here, well, can't do much with the 3, but the 81 is 3 to the 4. Okay, we've seen that a few times already. And then on the right-hand side, I know that this is going to be 3 to the 12x. So now, if the bases are the same and the powers are the same, I know the exponents must be the same. So I'll bring the 5x over. So negative 1 is equal to 7x. And I'll divide and I'll get negative 1/7 is equal to x. Okay, so I hope you're getting kind of a sense of the flow here, because it's just going to carry on. I'm just going to keep doing some examples here. Okay, one of the best teachers I ever had when we came to math was, he was so good because he basically just gave example after example after example, so that we had lots of things to look back on. Here, oops, what I've got is 3 to the x equals 27 times 3 to the 2x. So it looks like our common base here is going to be 3. So 27 will be 3 cubed. Then I've got 3 to the 2x. What I need this to be, though, is I need this to be power equal to power. So it's got to be single power equals single power. So on the right-hand side, though, now that I'm multiplying those two powers together, what I can do is add the exponents. So this becomes 3 to the, and I'm going to write it in this order, okay, 3 to the 2x plus 3. I'm going to add those exponents. Now I've got power equal to power. The bases are the same, so I can set the exponents equal to each other. And then I'm going to subtract x from both sides and subtract 3 from both sides to get 3 is equal to, sorry, negative 3, my mistake, is equal to x. Okay. Oh, now I'm looking here. No, that looks good. Negative 3 is equal to x. I'm looking at a scrap that I had done some work on previously, and I think I misread that originally and put the wrong value in there. Nope, that looks right here. Okay, so next we've got 81 to the negative x is equal to 9 to the negative x minus 2. This is an interesting question because normally when I look at 81 and 9, I'm reducing these things down to 3, powers of 3 here. But in this case, 81 is actually 9 squared. I don't have to go all the way down to 3. So this becomes 9 to the negative 2x is equal to 9 to the negative x minus 2. Now, this will still work if you take it down to 3. if you made 81 3 to the 4 and made 9 3 squared. But I don't need to. And now that I've got power equal to power and bases are the same, I can say that negative 2x is equal to negative x minus 2. Then what would I do? I would add 2x to both sides and then add 2 to both sides. So I would get positive 2 is going to equal x. And that worked out kind of nicely. All right, now over here, this could be a little tricky. This is one of those kind of questions here that if you're not really thinking about the rules, you could get caught on this one. 9 to the x plus 1 is equal to 1. Okay, that 1 is a little bit of an enigma to me. But when I think about it, and I think about the fact that, look, my emphasis here is on powers here. I want there to be power equal to power, and I want the bases to be the same here. Well, remember that I can write 1 as any base to the 0. So I could write this as 9 to the 0. In which case, once I've got power equal to power and the bases are the same, I can just set the exponents equal to each other and then bring that 1 over, and I get x is equal to negative 1. So I just want you to pay attention to the way that one worked here and how I was able to get that power to the exponent 0. You make that work there. It's a great little question. Okay, now this one right here, I've got already power equal power. The bases are the same, so I can jump right to x squared is equal to 4x minus 3. Okay, and I see that this is a quadratic, so I'm going to bring everything over to one side. So this will be x squared minus 4x plus 3 is equal to 0. And then I got to factor that. So x, what is that going to be? Factors of positive 3 that add to negative 4. Well, they both got to be negative. It's got to be 3 and 1. In which case, x minus 3 is equal to 0 or x minus 1 is equal to 0. So x could either equal positive 3 or x is equal to positive 1. Either one of those will work. Okay, here we go. Now, this is an interesting question. Because when I look at that, I've got 5, 2 to the x minus 1. And I want you to see that this here is a unit. Okay, that x minus 1 is an exponent. The base is just the 2, not the 5. 5 has nothing to do with it. And 40. Okay, well, there isn't a lot that's actually common here. In fact, I can't find a base that's going to be common to all of those. But one of the things that I can do here is divide both sides of that equation by 5 to start off with so that I isolate the power. And when you divide both sides by 5, on the left-hand side, that factor of 5 is going to become a 1. It's going to cancel to a 1. And on the right-hand side, I'll get 40 over 5, which is 8. Well, that's awesome because I know that 8 is 2 cubed. And so then I've got x minus 1 is equal to 3 because I've got power equal to power and the bases are the same. And then you'll simply add 1 to both sides and I'll get that x is equal to 4. In this case right here, I got a little bit going on. First of all, I noticed that 49. Now, it's probably, or it should be pretty obvious that the base here is going to be 7. Okay, so 49 is 7 squared. Now, over here, what I've got is I've got 7 to the 1 multiplied by, and I'm going to rewrite that square root of 7 as an exponent, as a power there. So 7 to the 1/2. So on the left-hand side, this becomes 7 to the 2x minus 4. On the right-hand side, I have to add those exponents together, and 1 plus 1/2 is going to be 3/2. And so now I've got, now I've got power equal to power. The bases are the same, so I can set the exponents equal to each other. Okay, I'm going to add 4 to both sides. And when I add 4, I'm going to need common denominator, so it's going to be 8 over 2. So 3 plus 2 plus 8 over 2 will be 11 over 2. And then when I divide both sides by 2, okay, and I know sometimes this gets confusing here, but when I divide, for example, when I divide 11 over 2 and I divide that by 2, this is the same as multiplying by the reciprocal. So my answer is 11 over 4. Okay. Another one here, number 13. Okay, so we got a little bit more going on. 1 over 4 to the x is equal to 8 to the x minus 1 here. Now I can tell that there's going to be a common factor or a common base of 2 here. 1/4 is going to become 2 to the negative 2. Negative because I see a reciprocal going on there. Squared because of the 4. And then over here, this is going to be, sorry, I did that. I was too quick with the 3. What I meant was 2 cubed to the x minus 1. So on the left-hand side, I got a power of a power, so it's going to be 2 to the negative 2x. And on the right-hand side, it'll be 2, and I got to remember to distribute the 3. It's 3 times that x minus 1, so 3x minus 3. Now the bases are the same, so I got to set the exponents equal to each other. Maybe I add the 2x to both sides. Okay, add 3 to both sides, and so I will get 3 is equal to 5x, or x is equal to 3/5. For question 14 here, okay, I got a lot going on here, but I recognize with the 2, the 16, and the 4 that these are all going to be powers of 2. So 16 will be 2 to the 4, and I hope that, like, the more you see these, the more automatic your replacements are going to be. Like you're just going to see the same numbers kind of show up over and over and over again. And so you'll get more and more used to what the replacements will be. So 2 to the 4x multiplied by, well, this is going to be 2 to the, remember I got to distribute that, 4x plus 12. Okay, it's 4 times x plus 3. So I got to distribute it. On the right-hand side, same thing. This will be 2 to the, I have to distribute that, 2x minus 2. Now, I don't have it as power equals power. I've got power times power equals power. But on the left-hand side, because the bases are the same, I can add the exponents together. So I get 4x plus 4x plus 12. So 8x plus 12 is equal to 2 to the 2x minus 2. Power equals power. Bases are the same. So therefore, the exponents must be the same. Bring the 2x over, bring the 12 over, and I'm going to get 6x is equal to negative 14. Almost there. I'm going to divide both sides by 6. Whoops. As soon as I said 6, I wrote the 6 here. It's going to be negative 14 over 6. And those are both divisible by 2. And then when I do that, I get negative 7 over 3. Okay. Now we're getting a couple other equations here that you should recognize. We did look at something similar to this before here. So I've got a 3, a 5, and a 75 here. And notice that they are not all powers of the same kind of common base here. But I can simplify this. I can get this power. I've got one really clear power here. I can get that power by itself by dividing both sides by 3. And when I do that, I get 5 to the x minus 3 is equal to 25. And 25 is, in fact, a power of 5. So I can now write the bases, these terms here as powers with the same base. Power equals power. Bases are the same, so the exponents must be the same. And then I will add 3 to both sides to get x is equal to 5. Over here, it's the same thing. 2, 3, and 18 do not have kind of a mutually common base that I can reduce them to. But I can divide both sides here by that 2, that coefficient, and I get 3 to the 2x minus 1 is equal to 9. Well, 9 is a power of 3. I can replace that with a power of 3, so 3 to the 2. Power equals power. Bases are the same, so I can write exponent equals exponent. And then I will add 1 to both sides, and then divide by 2. So x is going to equal 3/2. Okay, for this next question here, it says they want us to solve graphically for x to the nearest hundredth. Okay, so we've got 5 to the x minus 1 equals 10. And 9 to the 2x minus 1 is equal to 212. Okay, we're going to come back to this this screen in just a moment here. Just in a second here, what we're going to do is I'm going to transfer over and I'm going to show you how this would work on a calculator.
Okay, so here we are at the calculator. So what we're going to do, because we're going to do this graphically, I'm going to go up to y equals. Here are my options here, and I'm going to enter in my equation here. So 5 to the power of x minus 1. And I want to make sure that I've got that all in the exponent there. Now, for some of your calculators, after you press the caret symbol here, you're going to have to put parentheses down. If it doesn't move that up into the exponent, you're going to have to put parentheses around that exponent to make sure that it works. Then we move down to y2 here, and we're going to plug in 10. Okay? Now, when I graph this, if I press just zoom, if I'm working with my standard zoom settings, this is the graph that I'm going to see here. Notice that y equals 10 is riding just along the top here. Kind of prefer to see a little bit more of that. So I'm going to go into my window. And because it's right at the top of my screen there, I'm going to change my y max here to, let's say 15. So that now when I graph that, okay, yeah, that feels a lot better. I'm seeing that more in the middle of the screen here. So now I'll press second trace. These give me my options for what to do on the graph there. And I'm going to go down to intersect. Then I'm going to move my cursor close to that point of intersection. It doesn't have to be right on top of it. It can be, but it doesn't have to be right on top of it. The calculator is asking, am I on the first curve? I'll press enter to say yes. Did I jump to the second curve? I press enter to say yes. No, it's asking if it can use that number down there, that x value, as a guess. And yes, it can. Okay, that's okay. The guess is really about just getting to the answer quicker here. So if I just press enter right now, and I get this answer of 2.43. So that's the x value. Notice that the y value isn't relevant here. In the equation, there was no y value. Now, the next equation that we're supposed to solve there is 9 to the 2x minus 1 equals 212. So I'm going to go back into my y equals, and I will clear the equation. 9 to the exponent, okay, 2x minus 1. Come down to the next one, and it'll be 212. Now, as soon as I press graph here, I know this isn't going to work here. I know I'm not going to see the second graph at all because it's way, way up there. So I'm going to go to my window setting, and I need to make my y max bigger than 212. So let's make it 250. That should give me some extra there. So there's my graph. There's my point of intersection. So second trace, come down to intersect. And again, I'm just going to move my cursor over a little bit. Doesn't have to be right on the point of intersection. Press enter. Press enter. It wants to guess 1.66. That's okay. Press enter. And I get 1.72 when we round that to the nearest hundredth there.
So as we saw, x in this particular case here, whoops, sorry, I got to turn the pen back on here. X was equal to approximately, when you round it, to 2.43. And over here for this one, x was equal to approximately 1.72 when we round it to the nearest hundredth. Now, finally, this question right here says, when solving for x in this equation, 2 to the is equal to 4 to the 5x plus b, one possible equation could be. Now, bearing in mind what we've done thus far in this lesson here, it seems fairly reasonable to think that what they're expecting us to do is rewrite that 4 as 2 squared. Okay? Now, at this point, I don't see anything that matches that, particularly because on the left-hand side here, it's all 1, 0, 1, 0, and I've got a 2 here. So I'm just going to kind of plow ahead and see what happens. So here, I'm going to distribute that 2. So this will become 10x plus 2b. Ooh, now I'm seeing the 10x plus 2b, and I like that. So that's encouraging. But I still don't see the equation like what I've got here. But now, remember what I did here. If I've got power equal to power and base equals to base, I'm going to set the exponents to equal to each other. Now, on the right-hand side, remember, that's 10x plus 2b. On the left-hand side, remember, what is the exponent if it's not written? The answer is 1. And so in this case here, it's 1 equals 10x plus 2b, and that is answer A.